All right, but my first question to you is, does anyone know what the inverse of an exponential is? That's, yeah, very nice. It's a log function. Okay, so this would be a logarithmic expression or logarithmic function. Doesn't really matter which one you use. I'm not going to say logarithmic every time. That's quite a mouthful. I'm just going to call it a log function. It's absolutely fine. But when we are talking about the inverse of an exponential, what we're actually working with is a log expression or a log function. Okay, now there's a really useful little conversion rule that we use in order to convert between exponential and log and vice versa. And that is as follows. Right, so this is the little rule that we use. And what you need to realize is that the x's are the same, the b's are the same, the y's are the same. So basically, the base of your exponential expression or equation is the base of your log expression or equation. The exponent of your exponential expression equation is the answer to your log equation. And the answer to your exponential, whoopsie daisies, to your exponential equation is then the value of your log expression. So log base, whatever the answer would have been. So they all match up together. And this is going to be really important for us to be able to convert between the two, knowing which value to put where as we go along. So to start off with, like very, very basic, we're just going to practice converting. We're not solving for anything. We're not actually using the conversion in any way. We just want to practice converting, because if you can convert, it will obviously help you later. And then we'll have a look at how converting can help you solve different types of equations when it comes to log equations without a calculator. And when we eventually get to our function stuff, if we need to find the equation of an inverse, we know how to convert between the two. All right, so like I said, this is a very basic example to start off with. We would never really ask you something like this, but it just gets us into being able to convert. All right, so if we have a look at the first one, we've got 2 to the power 5 equals 32. All of that is true. We know that. Like I say, we're not solving for anything. We're just practicing conversions. So remember that the parts of your expression or equation rather here is this 2 is your base. This is your exponent. And this here is the answer to that exponential equation. So that should all match up with our log conversion rule. So if we look at our rule, we know that whatever our answer to our log expression is should be our exponent. So here our exponent is 5 is equal to log. The base of your log matches to the base of your exponential. So the base was 2. And the value next to that base is the answer from the exponential equation. So in this case, 32. So log base 2, 32 should give us 5. Now, obviously, guys, you can go and check this on a calculator if you wanted to. Just need to find my calculator. There it is. So if we bring up a calculator and you type that log base 232 in, you should get 5. Now, just very quickly, you've got 2 log buttons on your calculator. If you push the log button sort of on the second row of little ones next to the exponent, you get something without a base. Now, it's not that the base doesn't exist. This is a base of 10, so log base 10. This is useful when you're working with scientific notation, because remember, base of 10, so 10 to the power 2 or 10 to the power 3, you're then talking about scientific notation. Particularly useful, obviously, in science. We don't really use scientific notation a lot in maths, but this is a scientific notation log. So we don't want that one. We want the log at the top here with the 2 squares or the 2 rectangles. That gives us a base value and the value next to the log. See here we had log base 2, 32, and if we push equals, we get 5. So we can see that the log expression that we gave, sorry, I'm going to put the sharing back on now. The log expression that we gave here of 5 equals log base 2, 32 is correct. Okay, so again, we're just practicing converting, nothing super fancy. We just want to be able to do it. So I want you guys to try for me question B. I want you to convert 3 to the power 4 equals 81 to a log expression. Take a minute, see what you get. Like I say, you won't be asked to do this, but it is going to help you when we start solving equations, solving unknowns, finding the equations of inverse. Obviously, guys, remember you can put your answers in the chat. Oh, got it. Nice, guys. Okay, cool. So we want to take the exponent, which is 4, is equal to the base. No, it's not, sorry. It's equal to log of the base, which was 381. Now, if you want to put the 81 in brackets, that's awesome. Like, it's really up to you. You don't have to, you can, whatever your heart's desire. But we have managed to convert, and if you do go type log 381, log base 381 on your calculator, you will get 4. So you can double check yourself, but like I say, we're not going to assess it like this. This is just practicing that conversion so we can use it later. Okay, but where logs do become useful is solving for x without a, sorry, I didn't get to take a screenshot, I do apologize. Let's take a screenshot here while you're doing that. Where logs become useful is if we now need to solve an equation, particularly if we need to solve it without a calculator. Because if we've been given the log form, we can just convert it back into exponential, and we know how to solve exponential equations. So this is really useful when we do need to start solving for x-intercepts and y-intercepts and stuff like that, or if we have an unknown we need to solve for. And like again, the conversion from log to exponential or vice versa is really helpful. Right, so if we now look at example 2, we want to solve for x without a calculator, and in both cases, we've been given the log form. So what we would want to do is we would want to convert it back into exponential so that we can solve. So remember your little rule. And guys, this comes with practice. I'm going to be honest. I'm still not 100% comfortable converting between logs and exponentials. I don't know why my brain doesn't compute where things should match up. Can't tell you why, because it's not like it's particularly hard, but it comes with practice. All right, so you just got to keep practicing this stuff and making sure that you're comfortable with the conversion. And this is why I'm saying, give yourself a random exponential equation and convert it. Practice those things so that you are comfortable with it. Like I say, like it's taken me many, many years to be comfortable converting this stuff, and that's fine. You just got to practice. Okay, so just remember, this number here refers back to the base of your exponential, of your exponential expression or equation. This value here is your exponent, and this value here would be your answer. So if we now go and convert it, what we have is base of 2 to the power x is equal to 4. Exponential equation, we know how to solve this. Make your bases the same. 2 to the power x equals 2 squared. And so therefore x is equal to 2. Again, if you want to go type log base 24 on your calculator, you will see that it gives you an x value of 2. So you can double check yourself. Anytime you've got an equation, you can double check yourself. But just remember where all those elements are, how they match up in order to convert. And like I say, this comes with practice. If you can see it perfectly the first time, like really well done, because like I said, it's taken me years, but it comes with practicing. So again, if we match up everything that we know in the second one, 3 is our base, 2 is our exponent. This x value would be the answer to that exponential equation. So if we convert, we, excuse me, we've got 3 to the power 2 equals x. And so now x is equal to 9. Again, if you now go sub that back in and type log base 9 on your calculator, you should get 2. So this is particularly, or the conversion is particularly helpful when we need to solve for an unknown. And like I say, we start to solve for unknowns when we start working with functions and we start looking for x-intercepts, y-intercepts, etc., and converting to find the inverse function of either a log or an exponential, which we'll look at in a little bit. But before we get there, and you can screenshot that if you want, I want you guys to try those 2 questions over there. There's no instruction, which is not particularly helpful, but you're solving for x. I'm going to give you 3 minutes. I want to know the value of x in both of those equations, please, without a calculator. Okay, I'm going to give you 1 more minute. I'm liking what I'm seeing so far, though. All right. So I'll make it smaller in a second for you guys to screenshot everything if you need. If we have a look, so question A, if you convert it, you get x squared is equal to 9. Now, please remember, technically speaking, when you are solving for this unknown x, what you would technically do is square root both sides. So you would actually have plus minus square root 9 equals x. So technically x is plus or minus 3. But your base should always be greater than 0. It's the coefficient that is negative. So your base should always be positive, and so that's why we can say x is equal to 3 here. When it comes to question B, your x value here was 5 over 2. It makes sense that it's 5 over 2 because if you think about it, a base of 4 needing an answer of 32, we can't make that a prime base. So it makes sense that prime base, we can't make that sort of coexist with each other. You can't just get an x value nice and easy. It's going to have to be rational. I don't know if that made any sense. In my brain, it made sense. If it doesn't, just ask. But it makes sense that we should get a rational exponent here. Rational exponents as well, you did in grade 11. While it's not a huge section, I won't stress too much about it. If you don't know what I'm talking about when I talk about rational exponents, please do go have a look at your grade 11 stuff. All right, but if I just make that a touch smaller for you guys, there we go. If you want to take a screenshot, you can. And then what we're going to do is we're going to now start having a look at this in terms of functions. We're going to start by just recapping the absolute basics of exponentials. I did also remember put a little while ago when we started the section a summary of the characteristics of each of your functions from grade 11. So that is on Google Classroom. You can find it there. So we're just going to recap the absolute basics of exponentials, and then we're going to start looking at the inverses, which are logs. Okay, because obviously you can't do an inverse if you don't know what the original is. Okay. Right, so we're going to look at two scenarios, mostly because these are the two scenarios you will encounter when it comes to the inverse function. Sure, guys, I don't know if you can hear this child crying, but I do apologize if you can. It's not my child, some strange child, but I do apologize if you can hear it. Okay, so we're going to look at the first. This is your parent exponential function. So there's been no shift left or right, no shift up or down. The base is 2, because remember your base can't be 1 because 1 to the power of anything is still 1. So it is the absolute most basic parent function of your exponential. So that's what we've got here. F of x is equal to 2 to the power x. We want to sketch that just so that we are reminded of what that exponential graph is. Okay. Any exponential graph has got an asymptote. It is always a horizontal asymptote for an exponential graph. In this case, because the graph hasn't shifted up or down, our asymptote is technically our x-axis. Now, we don't draw it. Remember, if it's on the axis, you don't have to draw the asymptote. I'm just reminding you of that fact. And I am actually going to put it in here just so that we remember it, because there's something that quite cool. There's something quite cool that happens with your inverse function. And so this equation is y equals 0. Remember, x-axis equation is y equals 0, because all along there, the y coordinate is 0. You haven't moved up, you haven't moved down, it's at 0. Okay, if we wanted to then find the intercepts of the axes, firstly, there's going to be no x-intercept because that is the asymptote. The x-axis is the asymptote, which means it can't cut the x-axis. So we will only have a y-intercept for this graph. And remember, your y-intercept is where you make x equals 0. So this would be y is equal to 2 to the power 0. Any value that is not 0, that is raised to the power of 0, is 1. And so our y-intercept here is at 0, 1. Obviously, we want the shape of our graph. So this is how we start substituting in random values of x. I don't care what you substitute in, entirely up to you. If I substitute in x equals 2, we've now got 2 to the power of 2, which is 4. If you substitute in x to the power negative 1, so x equals negative 1, 2 to the power negative 1 is a half. Okay, so we get the general shape of our graph. I'm going to do my best to draw this as well as I can, and I did a really bad job. Yeah, slightly better. We're just going to roll with it. So this is our f function. Nice and easy, nothing too complicated. It is what it is. Just as a quick reminder here, the domain of your exponential function is x element real, because as you can see, it extends all the way to negative infinity, all the way up to positive infinity, x element real. Your range of your exponential function is from your asymptote up. If the coefficient was negative, it would now be underneath your asymptote, so asymptote down, but the range here would be y greater than 0. It relates directly to the asymptote. Okay, so that's our domain and range of this exponential function. The conversation around domain and range is obviously going to become important when we do inverses, because as we've discussed, they swap. We saw that in our last lesson. Right, I'll let you take a screenshot of this in a second. Let's have a look at the second type of exponential we can get. Also still very, very basic, no shifts. They can be shifts, but for this one, no shifts. But now where the base is a fraction. So something happens to the shape of my graph when my base is a fraction. Okay, no asymptote, so no horizontal, well, no, let's rephrase that. The asymptote for this graph is still at your x-axis because it has not shifted up or down. So we still have an asymptote on our x-axis, which means our asymptote equation is still y is equal to 0. But like I say, because of that base that is a fraction, something's going to happen to the shape of my graph. Because the x-axis is my asymptote, can't have an x-intercept, but I can have a y-intercept. So I'm going to do exactly the same thing, make x equals 0. So now we've got y is equal to 1/2 to the power 0, which means that y is equal to 1. So same y-intercept. That often happens with exponentials that haven't shifted up or down. But we've got a coordinate 0, 1 here. We now want some other coordinates. So let's say, for example, I substitute in x equals 1. X equals 1 would then give us 1/2 to the power 1, which is 1/2. So we've got a coordinate at 1/2. If, for example, I substituted in -2, I would now have 1/2 to the power -2, which, remember, flips my fraction. So it is actually positive 4. You can also do all of this on your calculator. You don't have to do it in your head like I'm doing. And so what we've got is our graph of G. So what I want you to realize, and whoops, I'll make it smaller in a second, is when your base is a fraction, the shape of your graph changes. Again, this is all in the summary notes I put on Google Classroom. You can have a look there if you don't remember the shape changes, but it's all there for you. Right, very quickly before I make it smaller so we can compare a bit more. The domain is still x element of real. It's extending from negative infinity all the way to positive infinity on your x-axis. Your range, it sits above your asymptote, so y greater than 0. So if you compare the two graphs that we've drawn, we have a scenario where your base is greater than 1, and so it's an increasing function. Again, this is all on that summary, but I'm just going to write it here just as a general thing here. So if b is greater than 1, we have an increasing function. If we have, weird, if our b value is a fraction, so b is between 0 and 1, what we have is a decreasing function. Right, so we should remember this all from grade 11. If you don't, the notes are there, go and have a look. But that is the basics of exponentials. Now, what's going to happen is that each of these two scenarios, an increasing and a decreasing exponential, can obviously both have inverses. And so we're going to have a look at the two scenarios whereby we get these inverses for these two different types of exponential graphs. So hoping you've got a screenshot there of those two. I am going to move down. I will make it bigger and we'll do a screenshot of everything just now. But let's have a look at scenario 1 where that b value is greater than 1. So remember, b value greater than 1, it means that our graph is an increasing graph. We can see this here on the figure below. So if you have a look, this is our f of x graph, that purple graph. And we've got two graphs here. So what we actually have here as well is our inverse function. So remember, the inverse is where we take the graph and we reflect it over the line y equals x. So here's my line y equals x in this orangey yellow color. And we can clearly see that that is the mirror image. I don't think there's any argument there. That's quite clear for us. Okay, but there's a couple of things that we start to notice, and this links back to what we spoke about in our previous lesson. So firstly, let's just talk about the graph of f. So the graph of f has a y-intercept at 0, 1. We can see this on the graph. We also can see that its domain, as we've already said, we wrote it down earlier, is x element real, and that its range is y greater than 0. Because remember, the x-axis is our asymptote. Didn't like that. Sure. All right, so here's our y equals 0. Okay, so that's everything we know about f. We actually did that already earlier when we drew the graph of 2 to the power x. But let's now have a look at our inverse graph. So now we're going to compare all of this information for our inverse. If we do exactly the same thing and we try and find a y-intercept, hopefully what you can see is that there's no y-intercept. The reason for this is because of that swap between x and y. Our asymptote was originally horizontal. The inverse now has a vertical asymptote. So the asymptote of the inverse function is actually now the y-axis, the equation x equals 0. So when we now talk about our asymptote, this is now our y-axis. I'm just going to write that there for us. Okay, so there's that swap. The x and the y swap, the asymptotes swap. Okay, so that's the first thing that we notice. The second thing that we should notice, or that we should remember, is that coordinate swap. So originally I had a y-intercept at 0, 1. If we swap that coordinate, we now have 1, 0. 1, 0 is an x-intercept. And so rather than a y-intercept, we now have an x-intercept at 1, 0. Again, because of that swap with x and y. If we go to our domain, so we're looking at the inverse function. This is the inverse function, in case that wasn't clear. This graph only exists from our y-axis to positive infinity on x. So it only exists for all the positive values of x. And that's because of where the asymptote sits, that vertical asymptote. So here my domain is actually x greater than 0. My range, however, is the graph starts all the way down at the bottom at negative infinity and is going to go all the way up to positive infinity. So these are y element real. And hopefully what you can see here, guys, is the fact that there's a swap. Let's maybe do a bit better here. The domain was x element of real. The inverse's range is y element of real. So they've done a swap. The domain and range have swapped. If we consider the original function's range, it was y greater than 0. The inverse domain is now x greater than 0. So the domain and range are swapping for your inverse function. And this is a point of information that you need to remember and that you need to know. I can give you an equation of a function and ask you without a sketch, without a diagram, what is the domain, what is the range? And because you should know what the original's domain or range is, you can get the inverses. So this is a really cool characteristic that exists and a really important one for you to remember. Okay, I will make this smaller again in a second. You can take a screenshot of everything. Let's just have a quick look at our second scenario where we have that decreasing function. So this is now where we have our b value that is a fraction. So it's between 0 and 1. You can see the graph here. It is this decreasing purple graph. Sorry, guys, I just need to have a cough. I've got a frog in my throat. Okay, so if we do all the same things for our f, for our f function. Again, we can see where our y-intercept is. So our y-intercept is at 0, 1. We also calculated that earlier, so that's nothing new. We know our domain is x element real. Again, we've done this all earlier, and our range is y greater than 0, because remember, the x-axis is your asymptote, and the x-axis has an equation of y equals 0. Right, so in terms of our asymptote, that's what we have. Y is equal to 0. That's your x-axis. Oopsie daisies. So what we're going to now do is we're now going to go consider our inverse function. And again, hopefully what we're going to see is all the same sort of characteristics that we saw earlier. So if we now consider our inverse function, it obviously does not have a y-intercept because the y-axis is now the asymptote. So our asymptote here is the y-axis. So it has the equation x equals 0. Which means it can't have a y-intercept, but because of that coordinate swap, we do have an x-intercept, and that is at 1, 0. And we can see that here. When we talk about our domain, it is only from the asymptote towards positive infinity, so x greater than 0. When we then talk about the range, it's extending all the way up from positive infinity, all the way down, so y element real. So, range was green. If we now have a look at the domain of my original, swaps with the range of my inverse. If we look at the range of my original, swaps with the domain of my inverse. We also see the swap in case it wasn't clear in the asymptotes. Okay, so the original asymptote was, the original asymptote was y equals 0. The new asymptote, x equals 0. There is this constant swapping of x and y. We also see it with the x-intercept and the y-intercept. So if you can keep this in your mind, you will be solid when it comes to inverse functions. All right, hopefully this is not too small, but here's a screenshot of both scenarios so we can bear it in mind as we go along. I didn't draw the line y equals x on the second one, sorry, but if you want to draw that in for yourself, you can. But these are the things we now need to bear in mind as we start to look at questions. So we're now going to have a look at the type of question I can ask you when it comes to this. Right, so let's have a look. Example 4 says the function f of x equals log base a x passes through the point 4, negative 2. Whenever we are given an equation and then a coordinate, please always remember that that coordinate that I've given you, so this 4, negative 2 situation, this gives us x and y values that we can substitute in. So always remember that when in doubt, you can sub in for x and y. Now, if we go back and have a look at what we've been given, we were given f of x equals log base a x. The only thing I technically don't know there is a, because I've got an x and y value through my coordinates. So when we now look at the first question, determine the value of a and hence the equation of f, immediately I know what to do. I'm going to substitute. So I've got y is equal to log a x. I'm going to substitute my x and y values. So negative 2 is equal to log base a 4. And this is where the conversion is really useful, right? This is where if we can convert now to an exponential, I can solve for a. So remember, this is our exponent. This is our base. This is the answer to that exponential equation that we want to set up. So now that I have all of that, I can go and convert to an exponential. So I've got base a to the power negative 2 is equal to 4. There's a couple different ways that you can deal with this, but remember a negative exponent is essentially saying that you have a fraction. So we've got 1 over a squared is equal to 4. I'm going to carry on up here. If I times both sides by a squared, I've got 1 is equal to 4a squared. Divide both sides by 4, I get a quarter is equal to a squared. Square root both sides, I get plus or minus a half. But remember, a is a base, so a needs to be greater than 0. And so a is equal to a half. So that's the first part of my question done. The second part said then find the equation. So f of x is equal to log base a half x. So once we have a, we've got the equation. We don't need to stress. It's getting a that might take a bit of work. However, the whole point of us doing all of those basic conversions at the start of the lesson was so that we could do something like this. So that, and remember I say to you, conversions help us solve for unknowns. We were able to solve for a here. All right, so that allowed us to solve for an unknown in my logarithmic equation, or my logarithmic function. It's also going to help us out in the next question. So it says, write down the equation of the inverse of f in the form f to the negative 1x equals. Now, whenever they give us a specific format that they want the answer in, please make sure you do use it. So we will need to have our final answer as f to the negative 1 of x, but we can get there. Alrighty, so, okay, technology. Our original is y is equal to log base a half x. Remember, the basics of any inverse, swap x and y. X is equal to log base a half y. And now we can use that conversion rule that I had earlier to convert this. So this x answer is the exponent, half is the base. So we've got half to the power x equals the answer y. There's my inverse function. We write it in the correct format. So f to the negative 1 of x is equal to a half to the power x. So always remember, inverse function, swap x and y, and then you can apply your rule. So I'm just going to write that down. So we need to swap x and y. And then we can apply the rule that says what I wrote down earlier. This was an excessively long arrow, but whatever. So please remember to do the swap before you go do anything else. Otherwise, you're going to get weird answers. Swap first and then apply the conversion rule. All right, I'm just going to let you take a screenshot here. There are more questions, but otherwise it's going to be quite small. So take a screenshot of those first 2 questions. As you can see, the next one says draw a neat sketch of the graphs. If you've got your screenshots or if you've got it all written down, you can get started on sketching those graphs. Otherwise, that's what we're going to have a look at next. Okay. Right, so we now want to sketch these 2 graphs, the original f and the inverse f of x. So f of x was log a half x. The inverse was that exponential we've just found, a half to the power x. Now guys, it makes no difference which one you start with. Personally, I would start with the exponential because for me it's easier to then visualize the inverse, but it makes absolutely no difference. We have also just spoken about the 2 different scenarios, and hopefully what you realize is that because the base is a fraction, we should be looking at 2 graphs that look like scenario 2. So those are the 2 sort of graphs that I'm expecting to draw here. But like I said, whichever one you start with, you start where you're comfortable. So I personally am going to start with the exponential. You also have a calculator, sub in values, plot what you want, you do you. I'm starting with the exponential. So the first thing I want to find is my y-intercept. I'm going to make x equals 0. So y is equal to half to the power 0, which is 1. So that's my y-intercept. Remember, you have to label all intercepts with your axes. We also know that the asymptote would be y equals 0. So the x-axis, we never draw it when it is an axis, but we know it's there. Right, so you don't even have to add the label there. we know it's there. If you want to add the label, that's fine. I'm going to leave the label there just to remind myself. Okay, so this is the equation that we're starting off with. I know that there's not going to be an x-intercept because of where the asymptote is, so I'm just going to sub in random points. If I sub in x is x is equal to 1 rather, it's half to the power 1, so that's a half. We have also sketched this graph, so it shouldn't be too confusing. If I substitute in -2, fraction flips, so it actually is 4. So I have got an inverse function that looks something like that. That is the best function I've drawn the whole day. Quite proud of myself here. Right, so there's the first one. Now I'm going to draw the inverse function, the log function, which is technically the original function. So make sure you're labeling correctly. Like I say, for me, it's easier to start with exponential, but it really makes no difference. As long as your labels are correct, who's going to know? So remember, because I now have one function, I just swap everything. So instead of a y-intercept, I now have an x-intercept because I've swapped those coordinates to 1, 0. We also have all those other coordinates, so you could just keep swapping them if you want, or you can substitute in values for x, whatever you want. I'm just going to swap the coordinates. So I had an original coordinate of 1.5, so now I've got half 1. I had an original coordinate at -2, 4, so now it's at 4, -2. And so my inverse function looks something like that. And again, label your inverse. Make sure you label all intercepts with the axes. So that's it. Because I knew in my head that I'm working with a second scenario where b is a fraction, I had a decreasing exponential, a decreasing logarithmic, I knew what I should expect. And so we were able to plot the graph easily. Remember, the logarithmic graph has got an asymptote at now x equals 0, the y-axis. You don't have to draw it because it is an axis. I don't know why I keep saying axes, but just remember it is actually there. Right. Question D asks you to write down the domain and range of each function. So I want you guys to try that for me by yourselves. I think you should already know what it is because we've been doing it quite a lot. But let's get down the domain and range. Bongi Nkosi asks, can you ask me draw the your English? Can you be asked to draw the line y equals x on this question? We can. You don't have to. And if it helps you to find your inverses, by all means do it. But we can ask you, but we don't really. We might not. It's not something that we do. I haven't seen it in the last 3-4 years. So not really, but we could. And then you can just draw it as a dotted line. Okay, so you're answering domain and range of both for me. And again, guys, we've done this quite a lot, so it shouldn't be hard. And if you are struggling, have a look at the notes from earlier. I'm going to give you one more minute and then we're going to have a look. Okay, let's see if we agree. We should. So if we consider the original graph which was the log graph, its domain is x greater than 0 because it's from the asymptote to infinity, whereas its range was y element real. If we now consider the inverse, which was the exponential, domain is now x element real, whereas range y greater than 0. Hopefully you're seeing the swap. If we're not seeing the swap, I'll help you out here for a second. So domain of the original becomes range of the inverse. Range of the original becomes domain of the inverse. Terrible color choice on my part, so let's redo that. But work with those swaps. That is the key to inverses. I cannot stress that enough. Right, if we go to question E is asking determine the values for x for which the function, so both of them, are either increasing or decreasing. Okay, when we decide whether or not a function is increasing or decreasing, we look or we read our graph from left to right. Sorry, I'm just going to do this. So that's really important. So left-hand side of my graph, oh, gracious me. Sorry, guys, technology, We go to the left-hand side of our graph and we read left to right. So if I start with my original graph, here I am on the left. As I read to the right, what I see is that my graph is decreasing. The same is actually true for my inverse. Here I am at the left. When I read to the right, my graph is actually decreasing. So both of these functions are decreasing, but it asks for which values of x. So if I go to my original, it is decreasing from the y-axis all the way to positive infinity. So this actually links with the domain. So it's f is decreasing for all x values greater than 0. If we consider the inverse function had a domain from negative infinity to positive infinity, so x element of real, and it's decreasing for all of those x values. Remember, it gets closer and closer to the asymptote, but it's still decreasing. So the inverse is decreasing for all x values. And again, it links to I don't know what I'm doing, sorry. It links to what the domain of your inverse function was. So because it was asking for x values and because the graph will only do one thing, it'll either increase or decrease, we can link it back to the domain of our function. So I'm just going to do that so that you can screenshot those. I can't remember if I said this. I think I did, but I'm just going to say it again. Please remember that I've uploaded a whole bunch of resources for you guys, so you can use those at your leisure, whether you want to or not, it's up to you. We are going to have a look at not more complex log graphs, but how these log graphs are actually going to be examined and tested in our lesson on Monday. So you'll get an idea of what to expect in a test or in exams, stuff like that. And obviously remember, guys, today is quiz day. In the chat, I've also sent a link there that is like a progress update. So just to like let us know where you're at, how you're feeling. Do you feel like you've made progress with your maths? Do you not? So if you can fill it out, it doesn't have to be immediately. It doesn't have to be today. I will also put it on the classroom for you guys to access. But if you can fill it out just so that we can see how you're feeling, where you're at in terms of your maths, that would be really helpful. And then, like I said, on Monday, we are going to step it up a bit, actually look at how this is going to be assessed and asked. This last question that we've just done is pretty much how these questions or these functions are assessed. But obviously, it's always good to see what past papers have asked in the past. And yes, that's pretty much where we're at. So once you've got the link in the chat, once you've taken your screenshot, I know it's a little bit early, but you do have a quiz. And like I say, like things are a bit hectic at the moment. So 4 minutes early is not going to be the end of the world. Guys, I'm hoping there's not going to be an issue with quizzes. I really am. We think we found the problem and I think I fixed it, but you know, technology will fight me. So if again you have an issue, just send the request access within 24 hours. It should be sorted. I'm really fingers crossed that it is now. Like I said, I think we figured out the problem, but anything's possible. Okay, but once you've got what you need, you are more than welcome to leave, and I will see you guys on Monday. So have an awesome, awesome weekend. Yeah, and good luck with the rest of the week. Kirsten, yes, I do. So number patterns, read the question carefully. And the reason I'm saying this is my matrix literally wrote a test on number patterns and functions today. And some of the questions they were asking me, it was just not reading the question properly. So read your question really carefully when it comes to sequences and series. My advice as well is know the characteristics of each. So for example, know that in arithmetic, first difference, quadratic, second difference constant, geometric, ratio. If you remember those things, that is essentially how you solve anything. All right. So when you're solving for an unknown, you're using that foundation of, okay, this is arithmetic, so I'm using the fact that the constant differences are equal. This is geometric, I'm using the fact that the ratios are equal.